on fundamentals of electrical circuits. As you might recall, we were on electrical circuits with dependent sources, and right now we are going into session 3. Session 3, of course, difficulty level continues to increase, but still it's okay because as you might have observed in the last 2 sessions, the dependent sources offer a very interesting concept that there are lesser number of variables, and so you can apply Kirchhoff's voltage law and current law in tandem such that you can solve the circuits. Okay, let's see for this particular circuit, that is circuit number 1 in this session, that is the 3rd session, wherein we have for the first time perhaps here an AC circuit. Okay, though it's an AC circuit, we need not worry because there are a lot of easy tips within the circuit. Okay, so let's start. Do we see dependent sources? Yes, there are 2 dependent voltage sources. The one on the left is J40 I2, so whereas I2 is the current in the second loop, that's in the right loop, and both these loops are now joined together only via a single line, or in other words, it means that they are independent with respect to each other, except for the fact that they have the same reference. Okay, this I've been repeating several times. Okay, similarly, let's move on to the next dependent source, which is 10 VL1, where VL1 is the voltage across the inductor with a reactance as given by J4. Okay, so though we have not gone into AC, you have learned AC, so let's use whatever knowledge we have in AC to continue with the solution of this problem. Okay, so now, and so what all do we see? What all are extra? There's an AC source Vs in the first loop or in the left hand loop, and there is a resistance, there is an impedance connecting between this source and the dependent source, which is 3 plus J4. Okay, 3 plus J4 offers a very interesting understanding that we can always have with us. That is, the impedance is going to be 3 square plus 4 square, the square root of that is 5, and the angle when it is 3 plus J4, it is 53.1. Okay, this we can remember at any point. That's even better to remember that. On the other hand, if it is 4 plus J3, that is, the impedance remains the same as equal to 5 ohms, but at the same time the angle becomes 90 minus 53.1, that is 36.9. So this is an important concept that you can carry even to the gate examination context. Okay, so that's one point that I wanted to make clear here. And then we move on to the other circuit, the other loop, wherein we see that it's a difficult impedance, that is, we have 5 ohms and J6 ohm reactance, or 5 plus J6 reactance, and then there is the loading resistor, which is 10 ohms. Okay, and so we have the 2 loop currents I1 and I2. Okay, and let's see what the problem is all about. Okay, in circuit shown below, if the source voltage Vs is equal to 100 angle 53.1, so remember 53.1 was also mentioned with respect to the impedance that connects the source Vs, okay, to the dependent source. Okay, then the Thevenin's equivalent voltage in volts as seen by the load resistance RL. So this makes us very free, because when you're talking about Thevenin's equivalent voltage, it means that RL has to be open circuit. That is, RL has to be removed and there's an open circuit. So immediately there are 2 repercussions, more than 2, but at least 2 right now. One is, of course, I2 becomes 0. If I2 equal to, because it's an open circuit, I2 becomes 0. So what happens, that the dependent source in loop number 1 or in the left hand loop becomes a short circuit, because the voltage source, it's a voltage source, and I2 equals 0, so it becomes 0. Okay, another important aspect happens to be that the impedance 5 plus J6 is not at all does not come into consideration at all, because if you want to find the voltage, the Thevenin's voltage after giving rise to an open circuit or removing RL, we see that the voltage across the dependent source is going to be the Thevenin's voltage, because there's no current flow through 5 plus J6, or in other words, there's no drop there. Okay, so only 10 VL1 needs to be found out. So let's move to circuit, the loop number 1. I hope this important aspect of connecting 2 loops via a single line, such that there is no interference at all, there is no current flow between them, but at the same time, because of the dependence, there is a voltage 10 VL1 there. Okay, So now let's focus on loop number 1. What do we see there? We see that now there is a short circuit there's a short circuit replacing the 10 J40 I2 voltage source, because I2 is equal to 0, and so now Vs is opposed by only the impedance 5 ohms with an angle equal to 53.1. So Vs is 100 angle 53.1 divided by the impedance, which is again 5 divided by 53.1. So there is a current flow as given by simply 100 by 5, 20 amps. Okay, and this 20 amps flows through 3 ohms. It also flows through J4. Okay, and creates the voltage drop VL1, on which the voltage source in the second loop is dependent on. Okay, so we see that J4, that is 4 angle 90 degrees multiplied by simple 20 angle 0 gives us 80, 20 for the 80 angle 90 or 80J. Okay, and then what is the Thevenin's voltage? As mentioned earlier, there's no drop across 5 plus J6, so there is only and the voltage 10 VL1, and we already saw that VL1 is equal to 80 20 for the 80J or 80 angle 90, so 80 into 10 800 angle 90. Okay, so option C is the solution, and it's actually very easy because of so many ease of doing problems that have been introduced in this problem. Okay, so let's move to problem number 2. What is this? Okay, so our attention goes on to the dependent source first, which is a voltage source as given by beta Vx. So there are two unknowns. There's a beta value and there's also Vx. Okay, so that's the difficulty level in this particular problem. Okay, what else is given? We have two independent sources, a 6-volt source on the left end and a 2 ampere source right in the middle, with so many resistors. All of them are different, so we can talk about 1 ohm, 2 ohm, 3 ohm, 4 ohm, etc. in easy manner. So there are two nodes as well. One is Vx, the other is Vy. Okay, so we can say that so it could be the voltages at nodes X and Y. Okay, so we can talk about the nodes X and Y. Okay, so let's read the problem. In the given circuit, for voltage Vy to be 0. That's very interesting. What does it mean? Vy is equal to 0 has again two repercussions. Let's see. Okay, the value of beta should be. Okay, so the value of beta needs to be found out. Okay, so Vx is already shown. That's the voltage at voltage across 4 ohms, because the lower branch is fully, or lower node is fully grounded. So the voltage across 4 ohms is Vx, and we have Vy equal to 0. Vy equal to 0 has again two important contexts. One is that if there is a current flow, of course there is a current flow 2 amps going upward, it has to be cancelled out. Okay, by virtue of two currents coming together. One is the current flowing from beta Vx through the short circuit, that's now there because Vy is equal to 0. So beta Vx by 3 ohms is one particular current. So beta Vx by 3 is one contributing to the cancellation of 2 amps. Okay, from the other side we are having a current coming from the 6 volt. Okay, so I call it as I6 volt. Okay, so now we have two currents totaling to 2 amps, both flowing downwards such that 2 amps can be cancelled. So beta Vx by 3 plus I6V is equal to 2 amps. Okay, as is written there. Okay, now let's go a little further forward. What do we how do we find out I6V? Okay, so what is I6V? That is 6 volt is now facing a network of resistances wherein 4 and 2 ohms are in parallel because of the short circuit. Okay, so because of the short circuit as indicated by Vy is equal to 0. So 4 and 2 are in parallel. So that means 2 into 2 by 3, that is 4 by 3. 4 by 3 and 1 are in series such that current emerges as given by 6 divided by 1 plus 4 by 3. Okay, and that's equal to 18 by 7. Okay, very simple arithmetic. Okay, and now what happens is that this current gets divided between 4 ohms and 2 ohms, and what we require is the current through the 2 ohm resistance such that you can add it to beta Vx by 3 and total it to 2 amps. Okay, such that the 2 ampere source gets cancelled. The current from the 2 ampere source gets cancelled. Okay, such that there is a short circuit between Vy and the ground. Okay. So now what's that amount of current? That is the current that emerges 18 by 7 multiplied by 4 by 6. 4 is the other resistor through which we are not computing the current. So current division rule. So into 4 divided by 4 plus 2, which is 6. Okay. So we see that I6 volt is equal to 12 by 7. So 12 by 7 plus beta Vx by 3 is equal to 2 amps. Okay, so at least let us try to find out Vx now. Vx is very simple because the current flowing through 2 ohms creates the drop at Vx because Vy is 0. Okay, so as simple as that. So we already got the current that is current contribution of 6 volt to the cancellation of 2 amps, which is equal to 12 by 7. So multiply it by 2. Such that we get the drop across 2 ohms, which is going to be Vx. Okay, so there's no more computation required. That's equal to 24 by 7. Okay, so we know Vx, we know beta Vx by 3 plus I6 volt, which is equal to 12 by 7 should be equal to 2. A simple arithmetic tells us that beta is as easy as 0.25. Okay, a good value. Okay. Okay, moving on to problem 3. Okay, yeah. So what is there? We see a dependent current source V4V1, and this V1 comes from the voltage across the 2 ohm resistor. Okay, and we see also that current Is is flowing into it. So Is is very easily V1 by 2 because V1 is the voltage across it created by current Is flowing through the 2 ohms. Okay. And we also have Vs there, that is so when the numerical value is not given, let's see what the problem is. And we have a network of resistors 2 and 3 ohms on the left side of the 4V1 current source, and on the right side we are having 4 plus 2 6 ohms. Okay, so let's add them together. It's equal to 6 ohms. Okay, unless required. Okay, unless otherwise required. Okay, so moving on to the problem reading. For the circuit given, the driving point impedance from the source in ohms. Okay, when you are talking about driving point impedance, you always go to those terminals. Okay, so what's the terminal? Terminal is where Vs is connected and it pushes the current Is into the circuit. So Vs by Is is going to be the driving point impedance. Okay, so now we need to find out Vs, and now we know Is as equal to V1 by 2, but still in terms of V1. So if we can get Vs also in terms of V1, a simple ratio would cancel out V1 and we would get what is called as the driving point impedance. So let's move on to the to more explanation. As usual in dependent circuits, it's best to see how the current distribution is. So 4V1 comes to the junction to the junction between all those circuits, and a portion goes to the 6 ohms, another portion goes to the 3 ohms. Okay, but 4V1 is also joined by V1 by 2, which is equal to Is. So we have two currents coming together. One is 4V1, another is V1 by 2, which is equal to Is, and then the total, that is 4 plus V1 by 2 is equal 4V1 plus V1 by 2 is equal to 4.5 V1. 4.5 V1 now distributes between the two resistors. One is 3 ohms, the other is 6 ohms. So it's easy to find out the current through the 3 ohm resistor. Okay, so we'll find out the current through the 3 ohm resistor. Why? Because we need to calculate Vs now. Okay, and Vs is on near to 3 ohms. Okay, so now what is the current through 3 ohms? It will be given by, as was done earlier, 4.5 V1 into the other resistor, which is 6 ohms, divided by 6 plus 3, 9. So this is equal to 3 V1. So if 3 V1 is flowing through 3 ohms, it creates a 9 V1 voltage across it with the direction as shown. Okay, or in other words, 9 V1 and V1 add together to create Vs. Okay, so now we have 10 V1 as equal to Vs. Okay, and we also know that Is is equal to V1 by 2. Okay, which was already spoken about. So Vs by Is will give you the driving point impedance as equal to 10 by V1 into 10 divided by V1 by 2, which is equal to 20 ohms. Okay, very simple problem. I hope it has been marked as answer B. Okay, from amongst the multiple choices given. Okay, so now I suppose we are ready to go to another problem, again with a simple connection between two circuits, or in other words 2 loops, such that the reference is maintained, but then such that the other points do have voltages, as is shown here, because here we see VAB right at the top between A and B, though we have a connection only between. Okay, so there's a voltage, there's no connection. Okay, at the top, but there's a connection at the bottom, or in other words there's a reference voltage. Okay, so now here this will be useful. Okay, so where's the dependent source? It is 4 VAB, and this VAB is now across A and B as shown between the 2 loops. Okay, so now let's look at the right circuit first, because we see right loop first, because we see that 4 VAB is a voltage source. Okay, and it is encountered by 3 plus 1 4 ohms. Okay, so or in other words there's a current flow, and it's independent of the current flow in the left loop, and it's equal to 4 VAB by 4 or VAB. Okay, so the current is also now called as VAB. Okay, so the current that is shown as I is equal to VAB. Okay, and what is required out of us is for the circuit given the current I. Okay, so this is what we are supposed to find out. Okay, so let's go to the now. So okay, so far so good. We see that current I, which is VAB, is flowing through 3 ohms. It is also flowing through 1 ohm and it's creating a voltage drop across the 1 ohm as given by VAB into 1 or VAB. Okay, so there's a voltage VAB across 1 ohm with the top terminal of B terminal positive. Okay, so now let's move to the left hand loop wherein we see that it's a DC source which is having a potential divider out of 1 and 1 ohm. Okay, so the voltage divides into 2 because both resistors are equal. So we have 2.5 volts across the 1 ohm which is standing vertically such that A terminal is now positive and it's equal to 2.5. Okay, so now we have all the voltages connecting between B and A. Okay, or in other words, VAB, where A is positive with respect to B, will be the same as equal to the other branches together, totaling to minus VAB. That is because B is made positive by virtue of the current flow in the left loop. So it is minus VAB, and then there is a potential rise across the 1 ohm resistor, and so it is minus VAB plus 2.5 equal to 2.5 volt. Okay, as divided by the potential divider. So minus VAB plus 2.5 is equal to VAB, or in other words, VAB is equal to 2.5 divided by 2, or in other words, I is equal to 1.25 because I is equal to VAB. Okay, so there's a small differences from other problems, but mostly the ideas remain the same. Okay, so in the 5th problem, let's see what is it all about. We see the dependent source 5I. Okay, it's a voltage source. So when it's a voltage source, then the Kirchhoff's voltage law becomes applicable. Okay, and when there's a current source, current distribution becomes useful. Okay, so now we have 5I there, and then there are 2 more sources. One is a 2 ampere source right in the middle, and on the left we have the 20 volt independent source. Okay, and we have 2 resistors, 2 ohms and 3 ohms, and 5I is dependent on I, which is the current which is emerging from the 20 volt source. Okay, so all very good. So yeah, so we see I emerging from 20 volt and then joining 2 amps and together flowing through the 3 ohm resistor. So it's equal to 2 plus I. Okay, and then it creates a voltage drop across the 3 ohms. Okay, which is shown as equal to 3 into 2 plus I. Okay, so now we can put together all the voltages as per Kirchhoff's voltage law and continue. Okay, so what is 20 volt equal to? It is the total voltage drops across all the across all of it. Okay, at the periphery. Okay, so we see that there is to balance 20 volt. On the other side we have 5I. We also have 3 into 2 plus I, which is equal to 6 plus 2I, and we also have 2I. Okay, so all of them are the same direction. So when you add them all together, we see that 14 is equal to 10I, or I is equal to 1.4. Okay, and what is required out of us is exactly the same. The current I flowing the circuit below shown in amperes. Okay, so I is equal to 1.4 amps. Okay. Moving on to the 6th problem, which looks a little complex, but it's actually very simple because if you look at the terminal or the node above 5 amps, it is connected to too many things, but at the same time it's not connected to too many elements. It's connected via a short to the 20 ohm resistor across it. Okay, anyway, let's see the different sources first. We have 2 dependent sources and both of them are dependent on Vx. Okay, and Vx is the voltage across the 20 ohm resistor that we were talking about. There is a current source 0.5 Vx. Okay, and horizontally displayed on the slide, and there's also a voltage source 0.25 Vx, which is again dependent on the same Vx. Okay, and we also notice the 8 ohm resistor across it, which is of no consequence, as was mentioned earlier. Okay, so these things I'm pointing out again and again such that you remember. Okay, so now what happens? Okay, so what is required out of it? Of course, there are other resistors. Unlike the 8 ohms, there is a 10 ohm resistor as also a 20 ohm resistor across Vx, which is telling us that there is a current through it. Since the upper terminal is positive, the current is entering to 20 ohms from the top, and that's equal to Vx by 20. Okay, so these things we know, and what is required out of us is that in the circuit shown the voltage Vx. Okay, so we need to find out Vx. Okay, so that's it. So let's analyze what happens to the 5 ampere current coming there, and what happens to it is that one part of it flows as the source current, the dependent source current 0.5 Vx. Okay, another part of it of course flows through the 20 ohm resistor as Vx by 20. And what is left, that is 5 ampere minus both these currents, flows through the 10 ohm resistor. Okay, so this is the partition of currents or distribution of currents as we see at the junction above or atop 5 ampere source. Okay, so let's calculate the current through the 10 ohm resistor as equal to 5 ampere minus 0.5 Vx, which is the current source which is going away, and there's also another current moving through 20 ohms, which is equal to Vx by 20. So, okay, so Vx by 20 is equal to 0.05 Vx. So this is the total current flowing through 10 ohms. Okay, once we have that, we can definitely set up the voltage equation as equal to, don't look at the 5 ampere source for giving you a voltage, but you know that there's Vx across 20 ohms. So Vx can be equated to all the voltages across it, which has two constituents. One is 0.25 Vx at the other end, and we also have in the same direction 5 minus 0.5 Vx minus 0.05 Vx into 10. That is the voltage drop across the 10 ohm resistor. Okay, so arraying them all together and doing the minor arithmetic that is required out of us, we see that 6.25 Vx is equal to 50, or Vx is equal to 50 divided by 6.25, which is equal to 8. Okay, so that's a good answer, and it is very simple. The only point that needs to be understood is that there is a current distribution from a 5 ampere source. One is the dependent source, another is the resistor across which there is a voltage on which both the current source as also the voltage source depends. And then what happens is that, so you can get the element through the current element through the 10 ohm resistor, and now put up all the voltages together. Ignore the 5 ampere source right now because you don't know the voltage across it, but you know the voltage across 8 ohms, so the 8 ohm is also inconsequential. You know that it's equal to 0.25 Vx. Okay, so moving on to the next problem, or the last sheet here. We have again, okay, it looks a little, okay, of course it's a nice problem, and I picked it from another source because it was very interesting. It looked very interesting because there are two dependent sources, 6ix2, which is a voltage source, and there is a current source. Again, it's 2 I by 2, and what is this ix2 and I by 2? Let's see. Ix2 is the current flowing through the 2 ohm resistor upward. Okay, and I by 2 is the current flowing through 1 ohm resistor downward, and in between we have the 11 amp source. Okay, and which has a voltage across it, which is given as Vz2. And what is required out of us is that we have to find the power delivered by the 11 amp source. Okay, so we need to find out Vz2. As simple as that, because once you have the power delivered, then you can multiply the voltage and the current and see that they are the same direction, and then find the power. Okay, so what do we have here? What all do we have? We know that there is a voltage across the 1 ohm resistor, which we were always discarding because it's across a voltage source, but we know that it is connected to I by 2. So we say that 6ix2 is equal to 1 into I by 2. Okay, so here we are having a usage for the resistor, which is normally discarded when we connect it across a voltage source, just because of the current dependence on the current source dependence, that is 2 I by 2 depends on I by 2. Okay, moreover, now we have connected between ix2 and I by 2 by saying that 6ix2 is equal to I by 2 into 1. Okay, I suppose that's the direction etc. all match. So that's the first understanding that we have. Now moving on to, let's talk about what is Vz2. It's the voltage difference between the two arms of the resistors. That is 1 ohm and 2 ohm. Okay, so what is Vz2 as shown here? It is shown as the left side is positive and the right side is negative. Okay, so let's collect all the voltages across it. One is across 2 ohms, but it's in the negative direction, so it is minus 2i 2 ix2, so minus 2 ix2, and then we see that, okay, so then we see that it's now going to be another drop, okay, because both are similarly oriented but in the opposite direction with respect to vz2. So minus 2 ohms into ix2 and minus 1 ohm into iy2. So minus 2x2 minus okay, so we are choosing 6x2, that's easier. So minus 2 ix2 and minus 6 ix2 equal to, so we are collecting all the ix2 together such that we can substitute there. Okay, so vz2 is equal to minus 2 ix2 minus 6 ix2, or which is the same as equal to minus 1 iy2. Okay, so anyway, that was already shown there. So vz2 is equal to minus 2 ix2 minus 6 ix2. I hope that's clear. Okay, now let's talk about what is the connectivity between the 11 ampere current and its consequent distribution. One flows through ix2, the other 2 iy2 joins it. Okay, so 11 ampere plus 2 iy2 will contribute to ix2, Kirchhoff's current law, or in other words 11 is equal to ix2 minus 2 iy2. Okay, so we have now two relations between ix. So now we can replace iy2 by what we already know, wherein we see that iy2 is equal to 6 ix2. So when you replace it, you see that you can easily calculate ix2 as equal to minus 1 amps. Okay, so once that is done, now you just need to fill up the equation vz2 with ix2 values, which is equal to minus 1, that is minus 2 ix2 minus 6 ix2 or minus 8 ix2 will now have ix2 is equal to minus 1. So we see that vz2 is equal to 8 volt. Okay, so now now it's very clear that there is that vz2 has the same direction as is shown. So it's not power actually delivered, but it is power delivered to because the current and voltage are in opposite direction. So it's the power delivered to the 11 ampere source, or it's minus that is so it's 11 ampere multiplied by the voltage, which is 8 volts. So minus 88 watts. Okay, so to the last problem in this session, we see again it looks a little simple because we have only one single dependent source, which is equal to 3 I1. Okay, and I1 is the current flowing through the 10 ohm resistor. Okay, and we also have a 2 ohm resistor at the other end. Terminal set is shown as AB, and a 5 ampere sources, an independent source 5 ampere is at the left edge. Okay. Okay, so what's asked is that for the network shown, the equivalent Thevenin's voltage and Thevenin's impedance as seen from across the terminal. So there are two parts to it as usual. When you are having Thevenin's impedance, you need both the Thevenin's voltage as also the Norton's current. Okay, so let's look for the Thevenin's voltage first. Open out the terminal AB. So now we see that the 5 ampere source has absolutely no way of flowing other than flowing through the 10 ohm resistor. So I1 becomes equal to 5 ampere. That's the first point. And so the voltage is also equal to 5 into 10, 50. Okay, and then it also creates, so now we have a voltage source there, but though no current flows to 2 ohms, there's a voltage source already there, which is equal to 3 I1. Okay, so 3 I1 means 3 into 5, 15. Okay, so the 50 plus 15, 65 volts is going to be the Thevenin's voltage. Okay, if you look at the answers, there's only one answer with 65 volt, so that is automatically the choice which is equal to B. Okay, but at the same time, let's try to find out the Norton's current also and get the ratio and obtain the Thevenin's impedance, because we may get such problems. Okay, further on. Okay, so let's short AB, and now we see that the current through the Norton's current is the same as equal to whatever flows. Okay, there's a current coming from 5 ampere source. I1 flows out of it. The rest will flow as the current through the 3 I1 source, as also that's a voltage source. So the current and voltage can be different, and then it also flows to the 2 ohms, and then it flows to the short circuit as the Norton's current. So 5 minus I1 is going to be the Norton's current. Okay, so that's first to be understood. Then we move on to what is called as the total voltage. Okay, so the voltage drop across AB is 0 because it's shorted, and we have a voltage across the 10 ohm source as given by 10 I1. We also have 3 I1. So 10 I1 plus 3 I1, which is 13 I1, is the same as equal to the voltage drop across 2 ohm resistor, which is equal to IN, which is equal to 5 minus I1 into 2 ohms. Okay, so put them all together. So now it's all 13I1 is equal to 10 minus 2I1, or in other words 15I1 is equal to 10, or I1 is equal to 2 by 3. Okay, so Norton's current is equal to 5 minus I1, which is equal to 13 by 3. Okay, so now we have 13 by 3 as IN, and we have 65 as VTH. Take the ratio, we can see that the answer is correct, which is equal to 15 ohms. Okay, so in this section, from amongst the dependent sources, we have been discussing how we can put together many bits of knowledge that we have, or general understanding of the circuit, such that as usual current distribution can be taken up first mostly, and then we can have the voltage configuration such that balance is possible and you can obtain some values. Okay, so mostly the comments mentioned for the for session 2 seems to, and 1 seem to be applicable for this session also. Only we have discussed a few more little problems with a little more difficulty level when compared to the others. Okay, I suppose still you realize that though the questions are trickier, the answers are even easy to find out. So long as you know the tips and certain aspects that you can easily use. Okay, thank you.